So, I am Mr. Brian Harrington, as you may or may not have been aware. So, this is going to be a talk about how CoreOS does its updates, as well as a little bit of an overview about CoreOS itself, the operating system. Kind of where our ideas were in, or what the ideas are in driving the development of it, and where we're going with operating systems for servers for the future. So, like I said, I am Brian Redbeard Harrington. You may see, something missing here in comparison to the photo. There was a number of comments on the Meetup. Looking forward to that. See, the problem is that I get associated a lot with these guys, and I really have no urge to be associated with that. So, I'll press the reset button and bring it back up, and then, we'll let them kind of have the limelight for a minute, and then I'll come back. But we're not here to talk about my beard. We're here to talk about CoreOS, and specifically containers and a little bit of the future of Linux and where we're going with that. So the big question that comes up is, why do this? Why? We want to secure the internet. That sounds like a really bold statement, but we're just going to throw it out there. We want to secure the internet. If you look at historically the way the internet has been managed from looking at security, there's a lot of absentee landlords. You start out with the brain virus in 1986, and everything's fine. There's no problem up to that point. But as things increasingly progress, there's more and more absentee landlords that just set up servers and then don't do anything. Or they start to set up servers and they run a few patches and then everything falls off. And the best way of summarizing that is that if we only cared enough, we could totally make the internet work. But caring alone has not actually gotten anywhere. Like, we tried that, and it's not doing anything. So we're back to the point where we want to actually proactively embark upon this and try to get something done. And, pivoting on this a little bit and looking at ways in which this has worked in other fields. If we use HTML5 as an example, HTML5 started to be ratified in 2011. And the projection was that by 2020, we will have HTML5. It's 2014, and it's pretty well here. How did that happen? Well, that happened through products like ChromeOS and the Google Chrome browser and Firefox actively pushing updates to their users. They said, users are great. Everybody gets annoyed at the little, click now to update. Yes, confirm. Yes, confirm. Yes, I agree. Yes, EULA. Keep going. OK, now you want me to reboot. And I lose everything that I was working for. So organizations started finding new ways of pushing their software updates. Even better, they open sourced the mechanism in which this was done. So CoreOS took a look at that and said, that's a smart idea. Why is everyone not doing that? So you look at this a bit more and go, well, what are the problems with a modern distro? Or what are the problems with Linux, from where it was conceived and where it starts as, kind of a fork from the ideology of Bell Labs Unix, and where do we get to today? So a modern distro packages all of these things together for you. They give you, a kernel and systemd and Docker and Python and Java and Nginx, and you're responsible for your app. Well, for anyone who's tried to use an enterprise Linux distribution, and the first requirement is, oh, well, my application, my developers, they wanted new shiny, so they did all the coding on Python 2.8. Well, your Linux distro only ships Python 2.7. And now if you want to try to swap that out, you're going to destroy all the utilities that the distro itself built to manage that Linux distribution. And it just starts to become this cascading failure. So what do you do? Well, it's actually really simple. You just move that line. When you start saying the things that are a part of my application, the things that matter become the interpreted language, the version of OpenSSL, the specific flavor of a database, then you're able to start saying, OK, well, there is a clear delineation here of what matters and what's stable and what isn't going to change. Linux Torvalds is very, very adamant about the fact that the kernel does not break user space. And then you post something to the mailing list going, aha, well, you're wrong. I did this problem. He goes, no, you didn't understand what you were doing. The kernel didn't break user space. You did. And this holds true to that. What CoreOS is at the very, very center of it is the Linux kernel. It's systemd to replace that sys5 init that is just been so troublesome for users coming from a Unix environment, but trying to live in a modern Linux world. And SSH so that you can get things done, and now Docker so that you can package things together so that you can combine your interpreted language, your application server, all of these. Now, you're not actually going to put all of those together in one container. The way that that's going to look is that you're going to have something that resembles more like this, where each host has these smaller containers running on it. And the container flavor du jour is Docker, and we support Docker out of the box. You want to run Docker, you set up CoreOS, and it's waiting for you. There's nothing else you have to do. You're ready to run Docker run commands and Docker pulls, and you're pulling stuff down from the Docker index, and everything's great. But we're also not beholden to that. We internally use plenty of stuff with systemd nspawn, and we are ready for wherever that container is going to go tomorrow. So as we progress from moving this line across from application to there, so that your interpreted language is ready to go with your application, there's a few other things that we want to talk about real fast. So CoreOS is not Chromium OS. It's not Chrome OS. It's not CROS. It's none of these other things. That's one thing that gets confused a lot on mailing lists. So we just want to be able to talk about that real fast. All of these share one common SDK. The big problem with building a Linux distribution is that you need to start from somewhere. We wanted to focus on building that secure Linux distribution, not on building a tool chain to get there. Well, the folks at Google, they wrote the tool chain. We're comfortable using that, so we might as well take those first steps and just go, sweet, somebody else is managing that. I can focus on actually doing the work that I want to do. Now, versus CoreOS and Chromium OS, there are similarities. I mean, they're self-updating operating systems. But Chromium OS and Chrome OS, they focus on desktops. They want to make sure that that desktop is up to date. They want to make sure that the user doesn't have to manage any piece of software. It's a browser on a computer, and if you can't get it done in a browser, move on. They're comfortable saying, if that's not the way you want to do things, then they're not the distro for you to use. We're saying we want to build a secure server operating system. We want to be prepared to make sure that the internet is ready for us and this secure distro. And how does this happen? That starts with the Omaha Protocol. This is the protocol that was created by Google that is the backing update service behind things like Chrome OS, behind Chrome browser, behind Google Earth. That's how, when you're running these pieces of Google software, they get the updates automatically to you. Now, this is an open protocol, but there's still, you need to actually implement that. And what we've done here is we've written open source bindings in Go, and they're up on GitHub. So anyone else now who wants to take this step and they want to be able to have an updater for their applications, or they want to be able to query for their literal application level code, we've got all the pieces up there today ready for folks to do that. We're trying to push this idea further so that now we have a secure self-updating operating system. You can have secure self-updating applications. And we're going to start working together with this ecosystem to make sure that everybody is prepared to secure the internet. But let's take a step back for a second. Let's keep it fresh. So what does that actually mean in this case? So what we're doing inside of CoreOS to, in this case, keep it fresh, so we've got this simple updater. And these are not things that are specific to CoreOS per se. These are things that you gain by using the Omaha Protocol for this. So you have a simple updater. The client itself is polling, not pushing updates. We say that, you push an update, but it's up to the client to say, hey, do you have an update? And the server says, yes, there is an update waiting. Here's where you go grab it. But the client itself is not forced into that. The client is in control. Now, the other thing that Omaha does in this case is it avoids, the kind of man-in-the-middle rewind attack. Now, what that actually looks like is where, I'm running version 5 of a piece of software. You're running, there may be a vulnerability in version 4, and the attacker wants to make you go back in time on that. It's really famous. Like the Nintendo Wii had so many vulnerabilities where if you could just get the firmware back in time, then you could, run these exploited versions of their operating systems that you could play, backup games and stuff like that. Well, that firmware or that consumer device, it's great that that happens. We want to make sure that this does not happen on the server side. And that's one of the things that Omaha does for you there. Now, the way that we break this down a bit further is that there's 5 basic components to this. So any application that is going to get updated is going to have some form of a UUID. And all that this is for is to correlate all the binaries for a single program which some customer would want to consume. Now, the groups are instances of an application which happen to be related. That might be some organization scheme. It might be a cost center. It might be an environment or a team. It's just, these are all specific groups that are all going to be running together. These might be systems in data center A and systems in data center B. These might be systems for, that the CEO's email is running off of and systems that everybody else's are. And the reason why you would want to do that is then we get into the idea of a channel or a track. We use the term channel. This is, one thing that's, a little bit of, wag the finger at us. We use the term channel because in the way which we express this to the community, it makes more sense. If you look at the straight Omaha documentation, like the way that the protocol spec is defined, they call it a track. That's one thing just to be aware of. But in our case, the idea of the channel or the idea of the track is, is it alpha software? Is it beta software? Is it stable software? And how this comes together is, well, now maybe the CEO, you force him to run stable. That way he never has any questions about whether or not his email is actually getting delivered on time. But, your team of 4 guys who's all running the CI system, you run alpha so that you catch those vulnerabilities or those bugs as soon as possible so that you can get ahead of fixing them. And now all of a sudden everybody within your organization is like, man, their software never has a problem, ever, ever. How do they do that? Well, that's one of the ways that you do it. You have canaries all throughout. And these canaries are the ones that you watch them die, and then when they die, you kind of go behind, and then you pull another one out, and everybody who wasn't paying attention goes, oh, that canary, it just lives forever. And finally, the package is just, it's the binary payload. It's the thing that actually gets downloaded by the clients and applied. And that's how all of these end up fully working together. Now, I realize that this is a little bit ethereal. So what we're going to do is we're just going to walk through what this looks like. And, it's a little bit of an awkward position because we're going to show you the actual request and response. That way you see it so that if you're looking through, you can pinpoint real fast all the things that are important in it. But it's down in the weeds. You don't really need to know this on a day-to-day basis. Really, being able to follow along at the 30,000-foot view is all that you need to understand this and be prepared to use this type of model in the future. So we start out. Client sends an application ID and the current version to the update server. So what does that look like? Well, we've got a little bit of preamble here that got cut off. Trust me, it doesn't matter. It's just saying, hey, this is the version of our updater. This is how I'm identifying. Think of it like, the user agent that you're sending across in an HTTP header. This is saying, hey, at the OS level, this is who I am. A little bit more detail. You're just saying the OS version that you're sending across. The important part here becomes the application ID. Now, this is a UUID that corresponds, this is a UUID that corresponds to our alpha channel. our alpha software that all CoreOS machines consume is an application. And its application that we track there is alpha. So in this case, the version that this machine was running is 289. This came off a live machine, by the way, a couple days ago. So it's running 289, and it's tracking the alpha branch of the software, the alpha channel of software. And then, there's a little bit of extra stuff where we have pings and, the update check. Important also down here, though, is the event type and the event result. Because if you actually start doing a TCP dump, you'll see periodic communications going back and forth. It's not a big deal. All that you're doing here is you're saying, hey, I am downloading this software. I am in the process of downloading, and that's my event type. And then my result is a 2. That means I successfully downloaded it. I was able to get that back. So, we sent that application ID. It told us that there was a version to update. And then the URL responds with the actual URL of where we get that update. So again, we have a little bit of preamble here. The line that got cut off just says response protocol was version 1, and that the server was, update.coreos.net. Nothing really interesting. But where things start really starting to make sense is you see URL codebase. Well, that's where you download it from. And then the file that you're looking for is update.gz. And you start getting back a size and expected hash so that, in the eyes of the original Omaha designers, you don't want to force authentication. You don't want to force SSL. You want the client to be given enough metadata so that they can do the attestation themselves. Because they were really gearing things towards embedded devices, small ARM processors, things like that. Well, personally, we're not beholden to that. We know that everything's probably going to have a robust network. It's probably going to have enough other things in place to handle making sure that the network's not just going to drop. It's going to be running an x86-64 processor. There's a lot of assumptions that can be made, so we leverage those. In addition, we hand back a SHA-256, so a better verification of that file, and then a cryptographic signature that can be verified so that so that the system knows that the software came from us. Now you have that combination of a cryptographic signature, a hash so that you can verify that there wasn't a problem in corruption with downloading, and that the file came from us and is safe to apply. So now that the system knows that that update is safe to apply, it goes and actually downloads it. It does that verification of the hash. It does that signature verification, and it commits it to disk. Now, this is where things get a little weird. A little weird for folks who have been living in the server world. For customers who I've worked with who do things with network devices, who do things with consumer electronic devices, they go, oh, that's the way we've been doing stuff for years. That makes perfect sense. You have a data partition where your actual files that make that system unique live. And then you have user partitions where your firmware, if it was a consumer electronic device, would live. And we have 2 copies of that partition, an A and a B. They're literally called user A and user B, like you'll see here in a second. So that update comes down. You see we're currently running on partition A. It commits that update to partition B, and then it does a pivot. The way that it does that, well, we'll talk about that in a second. This giant table, shows all of the actual layout. For folks who aren't familiar with GPT, the GUID partition table, one nice thing about it, you get a copy of the header and the table at the front end and the end of the disk. So if you're messing around and you accidentally DD the front of the disk a little bit, you still got enough to recover at the end. There's a little bit of a safety net. But like I said, most of this you don't care about. The parts that matter are those UUIDs, or those GUIDs, I should say. They're not actually UUIDs, on user A and user B. Now, one of the other things that GPT does is it defines GUIDs for known partition types. Most of you have been using this for a while. The GUIDs are defined for a Mac OS disk. They're defined for a modern Windows disk. They're even defined for FreeBSD and a few other types. And as more systems start using EFI, everything starts supporting GPT. Well, we leverage this in this case to say, hey, we are defining 2 known partition GUIDs for user A and user B. And now we can write a Dracut module that actually maps those to known devices so that no matter what CoreOS system you're booting, we know that it will be one of these two. And then we can pick from there to ensure that we're doing an update. Now, you go ahead and apply that update. After the updater runs the update and lets everything know that it's committed, it reports back. So again, there's communication going back and forth between that system during an update and our systems. The reason for that is basic telemetry. Telemetry, the idea that you have some inaccessible remote endpoint that is going to provide you useful information about the known health of something. You saw from the types of responses that are going back and forth, it's really just version information and enough like randomly generated unique IDs so that we are able to tell, in a worst case scenario, oh man, we pushed an update, which we are rate limiting, and we're not seeing a high success rate on that. Because one of the other things that this does is if a system commits that update and the update doesn't work, if it can't fully actually boot into that updated image, the system will reboot back and revert it to the known state. We've got these two read-only user partitions. Might as well use them. That gives you the ability to seamlessly go, whoa, buddy, I don't like the way that went, and revert back. That's what that's doing. So, we've signaled back that we are ready to reboot, and then that's what happens. We reboot. Now, yes, we reboot. Like that A-B partition layout, that's how we move from one to another. It's the reboot that performs that pivot. And the idea there is, well, what if my application isn't prepared for that? Sorry? We're in this pretty solid this second decade of the 21st century. Little startups down the road like Netflix are building applications which are resilient enough to have individual nodes shot in the head. We're not saying that that's, the right way of doing things. Yeah, let me back up on that. That's the right way of doing things. Your application should be able to handle the unknown. When the CTO of Amazon goes, hey, everything fails. Every piece of computer hardware fails at some point. You've got to be prepared for that. There's something to that. We had some failures today on systems, and it was Fleet which saved our bacon. We run Fleet internally for a bunch of our services. You are actually utilizing the end product of Fleet, and we are eating our own dog food here. So it's that unknown, it's that ability to recover from transient failures and permanent failures, some of which are in hardware, some of which are in network, that we're able to keep going with. So yes, we are going to take your system. Yes, we are going to force updates to it. Yes, we're going to force you to run things in containers. Yes, we're going to take away your interpreted languages. Do we expect you to be okay with this? Yes. That's where things are going. The best thing about Linux, to make giant blanket statements here, is that it's a bit of a menu. If you don't like the dish that we're serving, I mean, as one of the chefs involved, I'm going to shed a tear, but maybe you're not prepared. Maybe it's too spicy for you. I understand. But like you saw in Walden's thing, all the cool kids are doing it. But we're gonna take a second here. We're gonna take a brief moment for etcd. So that whole, what is etcd? It's a highly available key value store for shared configuration, service discovery, and distributed locking. Fortunately, Walden gave you a good overview of that so that you didn't need my marketing slide up there. The big thing is, the thing that we leverage here is that it ships on every single CoreOS instance. But more importantly, what this does is that we have a tool called Locksmith. Now, this is on all of the alpha images right now. For folks moving over to beta, it's going to be available, I believe, in the next release.
It's there.
OK, awesome. It's there today. And what Locksmith is, it's a reboot manager for CoreOS, which is backed by etcd, and it works in tandem with the update engine. So that update engine, which is going and talking to us and going, hey, is there an update? Yes, there's an update. Locksmith is the thing that actually handles telling the system to reboot. Now, can you just turn off Locksmith and no longer have your system automatically reboot? Yes, you can. Do I recommend that? No, I do not. But yes, you can do that. Now, the important thing here is that what Locksmith is giving you is that it brings in the idea of a configurable strategy to how your update happens. You know, what that means we'll get into in a second. But the most important thing, if I was to just summarize this in one thing, is that it gives you a semaphore for your reboots. You know, for folks who are not familiar with the programming concept of a semaphore, it's a turnstile. It makes sure that one thing gets access to a resource at a time. Now, in our case, with the tunables, we give you the ability to not only allow one thing. You can say, oh, well, in my specific case, my unique case, 2 machines can reboot at a time. 3 machines can reboot at a time. You know, maybe you've got 15 or 50 machines in your cluster. And having them do this serial reboot process for the updates is just going to take way too long. In that case, yes, it makes sense to increase the maximum number of machines that can reboot at a time. Now, in discussing these strategies, there's 3 basic ones. You know, we'll start at most conservative, which is the etcd lock that says only reboot after you have successfully taken a lock on the system. Pretty simple. You know, if you couldn't take a lock for some reason, if there was a net split, if etcd was down, if something else was going, it says fail to a safe state. Now, other end of the spectrum there, we've got reboot, which is just fast and loose. I don't care. As soon as the update's ready to go, roll the dice and go for it. That's going to be good for you if you don't have applications that are deployed via Fleet, where it's just a large-scale component. You know, if you're using the etcd lock, as a machine comes down, it will notify Fleet and tell you, hey, you should reschedule this somewhere else. And then through the use of an ambassador with it, you can actually update a load balancer or something else to guarantee that those applications kind of have zero downtime on it. And then the middle of the road there, the one that we ship by default, is the best effort. It's best effort service. If you can't get a lock in etcd, like, you should really try for it, like really try to make sure it happens. But if it doesn't work, well, don't just hang there, like not updating yourself. Fail to a state where you're actually getting updates. So talking about this again, in review, what we've got is you've got a client that sends an application ID and a current version to our stuff. We respond with the update saying, hey, this is where you actually go retrieve it from. This is the information about the update. This is the metadata. This is the cryptographic signature. The client then retrieves all of that and parses the metadata and does something useful with it, which in our case is writing to the disk. If you wrote something to use Omaha Protocol, maybe it's running a script. Maybe it's doing something in addition. I mean, one of the nice things about Locksmith is that there's a tool called Locksmith CTL where maybe your application has a very specific process of what needs to happen. Using something like Locksmith CTL means that you can have a very customized strategy with that. It's not one that we ship, but all of these pieces then link together. So final step there is that the updater is going to give back some response code and then send it to us, and then it moves on. So Omaha Protocol is the oomph behind our updates. Reboots are needed to apply the patches, but Locksmith makes that process much, much less painful. So if you need help with this stuff, if you need to know, if you've got esoteric questions or you just want to, talk to me on IRC a bit, pound CoreOS on Freenode. There's also the CoreOS user and CoreOS dev Google groups. There's also the etcd dev Google groups. And then, little bit of additional thing in there. We do have a paid pilot program. If you want to see me come in and do a song and dance for your guys and teach you about this in a one-on-one or a small team basis, we are happy to do that. You will more than likely get me doing it. Like my purpose here is to make sure that folks in the community and that our customers are successful with this.